Ladies and gentlemen, my name is Lubomír Hříha, and on behalf of my colleagues Milan Jaroš, Petr Strakoš and Matěj Špečko from IT for Innovation's National Supercomputing Center in Czech Republic, I would like to present you our work entitled Path Tracing of Massive Scenes in Blender on Multi-GPU Systems. This is the outline of my talk. I will start with motivation and state of the art. Then I will present you our new method that enables rendering of large scenes on the GPUs. Finally, I will conclude the talk by demonstration of the interactive path tracing of large scene, and at the very end I will show you a short video about our new add-on for Blender used to import Moana Island scene. In this talk, I present a solution for path tracing of massive scenes by combining the performance and, most importantly, memory of multiple GPUs. In recent years, the advances in GPU technology made GPU rendering popular for its superior performance. On the other hand, the significant drawback of GPUs when compared to the CPUs is the limited memory size. As an example of massive scene, we use the Moana Island scene released by the Walt Disney Animation Studios in 2018. It was selected due to its uniqueness and wide acceptance by both industry and research communities. The majority of film production rendering systems rely on path tracing. The systems like Hyperion, RenderMan, Manuka, or Arnold almost exclusively use CPUs to render the final image. The reason is quite simple. The scenes are too large to fit into the GPU memory, as they can be easily larger than 100 GB. There are two possible solutions for the limited local memory. The first one is to use an out-of-core technique. The second one is distributed or parallel rendering. In case of parallel rendering, there are two different approaches: data parallel rendering or image parallel rendering. Our approach falls into the second category, as initially distributed scene data are moved between GPUs on demand, while ray data remains fixed. Our contribution lies in the method that minimizes these on-demand data transfer between GPUs during the path tracing process. Our implementation relies on CUDA Unified Memory technology and its implementation for multi-GPU systems. CUDA Unified Memory behaves as a distributed shared memory system. In such multi-GPU system, each GPU has a local memory, and there is a hardware or software layer which transparently creates an illusion of global shared memory with non-uniform memory access. The problem with performance point of view is that each GPU has a fast access to its local memory and slow one to the memories of the other GPUs. For such systems, the optimal performance when working with distributed data is achieved only when smart replication and migration techniques that improve data locality are used. In multi-GPU environment, CUDA Unified Memory allows us to break memory allocation into chunks, and for each chunk we can define in which GPU the chunk is stored or whether it is replicated in memories of all GPUs. Even though we can significantly reduce the communication between the GPUs, as we show later, it is still necessary to have fast interconnect between GPUs, such as NVLINK. We have developed our approach on state-of-the-art multi-GPU systems like NVIDIA DGX2 or DGX A100. If we look at the system like DGX2 from the parallel rendering point of view, we see a system that should be able to render massive scene of sizes up to 512 GB in the shared memory of its 16 GPUs. The next generation, the DGX A100, has 8 GPUs with 40 GB of memory per GPU, which results in 320 GB of total GPU memory. The uniqueness of both platforms lies in their NVLINK interconnect enhanced with NV switches, which is able to interconnect all 16 GPUs at very high bandwidth and low latency. The performance of the NVLINK interconnect in the DGX A100 compared to the bandwidth and latency of the local GPU memory is shown in these two tables. We can see that even though the NVLINK bandwidth is approximately 5 times slower than the local memory bandwidth, it is still very impressive 250 GB per second, which is comparable with memory bandwidth of today's CPUs. Together with very low latency of approximately 10 microseconds, this is the hardware technology that enables the successful implementation of our method. For implementation of our approach, we have selected Blender Cycles. Blender is a popular open source 3D creation suite with production renderer called Cycles. Cycles is an unbiased renderer based on unidirectional path tracing that supports both CPU and GPU rendering. In terms of GPU rendering, Cycles supports CUDA, optics, and OpenCL technology. We have selected Cycles as it is a high quality and very complex renderer with large community. As the DGX systems do not use GPUs that are commonly used in computer graphics, we show this slide which compares the performance of a single P100 and A100 GPUs with GeForce or Quadro RTX GPUs in standard Blender benchmarks. The key difference in using the GPUs designed for HPC market is that they do not contain the RTX cores. Let's suppose we have a scene prepared for path tracing, which is stored in several data structures. Using CUDA Unified Memory, each data structure can be either replicated on all GPUs or distributed. Without any detailed knowledge about the data structure, we can use two different types of distribution. The continuous distribution, which split the data structure in large chunks and assign one chunk per GPU, or the round-robin distribution, which uses significantly smaller chunk of constant size and assigns multiple of these chunks to each GPU in a round-robin fashion. The first replication scheme I would like to present is on the granularity of the data structures. In this scheme, selected data structures are replicated and remaining ones are distributed. We have analyzed which data structures in Blender Cycles have the highest number of memory accesses as shown in this chart. We can see that these data structures covers over 95% of all memory accesses and at the same time corresponds to only 40% of the total scene size. The second chart shows the impact of replication of these structures on the scalability of the path tracing. We can see that path tracing on 8 GPUs is only 1.2 times slower when compared to the fully replicated scene. The problem with this approach is that it still replicates a significant part of the scene, over 40%. Based on our hypothesis that not all parts of the data structures are accessed evenly, we have developed the advanced method presented in the following slides. Before I introduce the method itself, I would like to highlight one key feature. This method works on a memory management level, which means that it doesn't matter what is the content of the data structure. It simply takes a GPU memory allocation, breaks it into chunks of predefined size, and for each chunk defines whether it is replicated or distributed and in which GPU memory it is stored. This makes our approach applicable to any CUDA-based path tracer without any modification of the path tracing kernels. The only changes in the code must be done during the allocation of the device data structures. Let's suppose that we have all data structures divided into chunks. Then, in the first step of the algorithm, we divide scene into partition based on the screen partitioning. In the final rendering, each of these partitions will be rendered by a different GPU. The second step of the algorithm is to analyze the memory access pattern of the path tracer based on one or more samples per pixel prepass. This step is performed for each partition independently, and it can be done either on a CPU with enough memory or on a multiple GPUs where all chunks are fully distributed in a round-robin fashion. The output of this analysis is an array of memory access counters, one counter per chunk per partition. In the third step, we select chunks which will be replicated. At first, we sum all per partition counters so that we get total number of accesses to each chunk for all partitions. Now we select the chunks with the highest number of accesses and mark them for replication. The number of chunks that are marked for replication can be easily calculated from the scene size and the total amount of the GPU memory. In the fourth step, we distribute the remaining chunks that are not replicated. Our goal is to place each chunk to the memory of the GPU that has the highest number of accesses to it. This step is done based on the per partition counters. As shown in this example, the chunk has most accesses from the second partition from the top, and therefore it will be assigned to a GPU number 2. There can be chunks that have no memory accesses at all during the one sample prepass. These chunks are distributed in a round-robin fashion evenly among all GPUs that still have free memory. And this is the final distribution of the chunk in our small example. The white spaces in the representation of the memory of individual GPUs show the memory capacity saved by chunk distribution. This is a visualization of the distribution of the data structure that stores vertices in cycles. On the left, we see an example where the data structure is fully distributed. Each color represents one GPU, and one can see that the colors follow the screen partitioning. The individual partitions are denoted by the bars on the right-hand side of the picture. The two pictures in the right shows the situation when 10% of the data structure is replicated. The replicated parts are represented by the origin colors of the final image. The distributed parts use the same color for individual GPUs as for the fully distributed scene. And this is a visualization of a distribution of the BVH tree for different levels of the tree. Different colors represent different GPUs, and the white color represents replicated chunks. The screen partitioning is denoted by the color bars on the right side of the video. In this slide, I show a little bit of implementation details on how a memory allocation in the CUDA unified memory can be partially replicated and partially distributed among memories of multiple GPUs. This is a code that is with small modification applied to all data structures in cycles that are in the GPU memories. I do not want to run into too much details. If you have any question, please do not hesitate to contact us. This chart shows how much memory accesses is covered by the replicated chunks for the different replication ratio. The most important fact is that the larger the scene is, the smaller part of it must be replicated. For Moana Island scene of size 169 GB, we need only 5% of replicated chunks to cover 95% of the total memory accesses. This is a significant improvement over the method which replicates the entire data structures. Finally, let me show you the performance evaluation for massive scenes. The first test scene is Moana Island scene of size 169 GB, where 90 GB is geometry and 58 GB are textures. This slide shows that even though the memory access analysis is performed on single sample per pixel, the rendering time grows linearly with increasing number of samples per pixel. This proves the usability of our method in production rendering. Our approach can be also used for interactive path tracing of very large scenes. This video shows the performance of the interactive path tracing on the DGX2 system. This is the second large scene we use for evaluation. It is an interior scene with following parameters. And we have the interactive path tracing demo also for the museum scene. In this talk, I have presented an approach that enables GPU rendering of massive scenes. The key contribution of our method is that it maintains the performance of GPU path tracing, and on top of that, it combines the memory capacity of multiple GPUs to be able to work with large scenes. I have showed the performance on Moana Island scene of size 169 GB, and for such scenes, our replication scheme needs only 1 to 5% of replicated data. I have also demonstrated very good scalability of our method. What is also important to mention is that our method works well also on lower-end multi-GPU servers with peer-to-peer NVLINK interconnect. The results for such platforms, together with more details, can be found in our paper. And finally, since I have a few minutes left, let me show you a video about Moana Island Scene Loader add-on for Blender. To be able to use the Moana Island scene dataset, we have developed an add-on that imports the scene data into Blender. The Moana Island scene dataset contains several formats, such as JSON with screen description, OBJ files with geometry description, and ptext textures. The developed Python add-on contains extension to C++ for faster reading and processing of the files. But still, importing the whole scene takes approximately 40 minutes. This video shows how to import only some parts of the scene, like the dead palm or a tree. The biggest challenges we had to solve were creating the instances and importing the textures stored in ptext format. We use Blender Hair system for managing the instances. We create a patch for keeping each instance in the right place. Then we use particle edit mode for baked hair, for which we have created another patch for faster baking. The next challenge was to import the PTEX textures to the Blender, as it doesn't support this format. We decided to write our own converter, which converts PTEX files to OpenEXR with UV system. In terms of lighting, we use only one light source, as the sun, and the HDR environment texture. I would like to thank you for your attention, and if you have any question, please do not hesitate to contact me on this email. Thank you.